Okay, everybody. Hey, I miss you guys, and I hope we can be together soon. I just want to take some time to go through these equations here. If you're struggling with this, please don't get too discouraged. This can be kind of difficult, especially when we're not in the classroom together and not in the lab together. Ordinarily, you guys would actually be doing these reactions, and I'd be kind of walking around helping you and whatnot. So it's a little bit tougher to do it this way, so that's why I wanted to kind of make this video. Also, on that same note, Monday, I'm setting up Zoom sessions for each class, 9 o'clock for second hour and 2 o'clock for eighth hour. And if you can join us, we're going to do this same kind of thing that I'm doing on this video with that third set of equations, part 3, that is due Friday. Anyway, let's just jump right into it here. Now, on these first 3 here, I went ahead and told you what the kind of a reaction is. So a single replacement reaction. By the way, these go with the videos. You may want to go back and look at those videos just to kind of refresh your memory a little bit. But I'll talk about what was on the video as well. So for the first one, we had hydrochloric acid. And hydrochloric acid, of course, is always going to be a solution. An acid is going to be in solution. And we added to that magnesium. And if you remember, the magnesium was in a balloon, which may have seemed kind of strange at the time. But if you recall, what happened, of course, was that this reaction gives off a gas. And that gas is what filled up the balloon. That's the reason I had the balloon. I wanted to collect that gas because the gas was used for the next reaction, the synthesis reaction. All right. So, single replacement reaction. What happens in a single replacement reaction is that one element, the element that's by itself here, the magnesium in this case, is going to replace an element in the compound here, the other reactant. And the way this works is, since magnesium is a metal, it's going to form positive ions, cations. So it has to replace the cation in the other compound. So it can't replace the chlorine because the chlorine can only make negative ions, and the magnesium cannot. So the magnesium has to replace the hydrogen, which means the hydrogen is now kicked out of the compound. So that gas is indeed hydrogen. Hydrogen, you may recall, is diatomic, so it's H2, and as I just said, it is in the gas state. Okay, so we've got H2 gas. That's what fills up the balloon. And the other reactant, the other product then is going to be the compound between magnesium and chlorine. In other words, in the single replacement, the magnesium kicks out the hydrogen, and now the magnesium makes a compound with chlorine. But we still have to balance charges. Magnesium is a +2 in the second column. Chlorine is a -1 as a halogen, so it is it's going to need a 2 subscript. So MgCl2 is the magnesium chloride. Now you may recall from the video, you don't see the magnesium chloride, and that is because it is dissolved. It is in fact an AQ. Now the last thing we need to do here is balance the equation. We've got 2 hydrogens and 2 chlorines on this side, and we can fix both of those things by putting a 2 out in front of our HCl. And now it's all balanced up. So again, single replacement reaction, we have a compound and an element by itself. That element replaces an element in the compound, and now we have a new element by itself over here, and we have a new compound. Okay? Now, the synthesis reaction. Remember, as I just said, we took that hydrogen gas from the balloon, so you kind of had to know that was hydrogen gas in the balloon in order to kind of figure out this synthesis reaction, which is another reason it makes it a little bit tricky. So we had that hydrogen gas that was in the balloon, and we had a bit of an explosion, right? In other words, that gas is burning. It explodes. It burns. And when something burns, it usually means, almost always, not always, but usually means that it is reacting with oxygen. Oxygen's another diatomic, so it is O2. And some people speculated that, the most likely product here, or the easiest product, would be just, if we have H2 reacting with O2, then we produce H2O2, hydrogen peroxide. Well, that's not quite right. That would make the balancing a little easier, but in fact, it's actually just H2O. That's the much more common substance. There's a reason why there's a ton of it around on Earth, is because it's a very common compound. It's a very easy compound to make. These things really want to be together, the hydrogen and oxygen forming those water molecules. We don't see the water, of course, because it's takes place because of an explosion. It's at a high temperature, and therefore it is in the gas state. It's actually water vapor. Okay. Synthesis reaction, I sort of skipped over that here. Sorry about that. Synthesis reaction means that we have multiple reactants, but only one compound as our only product. That's the key characteristic of a synthesis reaction, is that you have just one compound is your only product. Okay. Now we still have to balance this one up. We've got 2 oxygens on the reactant side, but only 1 oxygen on the product side, so we need to put a 2 here. But of course that gives us 4 hydrogens, so we need a 2 in front of H2 over here. Okay, so that's our synthesis reaction. Again, multiple reactants, usually 2, but it could be even more than that, and one compound is the only product. That's how we can recognize a synthesis reaction. Or in this case, you're told that it's a synthesis reaction, so you should know that you're only going to have one compound as our only product. Finally, our third one here, double replacement reaction. Double replacement reactions usually look a lot like this. We start with 2 ionic compounds in solution. In this case, we had silver nitrate, a nice clear colorless solution, so that's an AQ. And we had potassium chromate. Potassium chromate is K2CrO4. Chromate's a -2 ion, and potassium's a +1. So that's why it's K2CrO4. That is in solution. It has a yellow color, but otherwise it's nice and clear. It does have a color, but it is clear. So what happens in these double replacement reactions is we've got 2 ionic compounds, and one cation is going to replace a cation in this compound, but at the same time, the cation from this compound is replacing the cation in this compound. So in other words, basically they switch partners. We've got 2 ionic compounds that essentially just switch partners. And so now that means that the potassium is now going to be with the nitrate, and the silver is going to be with the chromate. Now we've got to clean this up a bit, because silver is a +1 and chromate is a -2, so that means we need Ag2CrO4. Potassium is +1 and nitrate's a -1, so that one's okay. So now we have to balance this a little bit. And that means, well, if we have 2 silvers on the product side, we need 2 silvers on the reactant side. And that gives me 2 nitrates and 2 potassiums. And so that means I need a 2 right here as well. Now the last thing I need to do to this one is decide which one of these is a precipitate. You may recall, or if you watch the video again, you just saw that when I put that yellow potassium chromate into the clear colorless silver nitrate, I get kind of a reddish brown precipitate. A precipitate, remember, is a solid. It is something that does not dissolve. So the bottom line here is that one of these compounds, one of these products one of these compounds on the product side is still dissolved, is still an AQ, but the other one is a solid. It's a precipitate. It does not dissolve. So we have to figure out which one that is. Well, if you remember, on the back of the periodic table, underneath all those polyatomic ions, there are what are called solubility rules. And it's basically just a set of rules. On the left-hand side, it says, if a compound contains these things, it's soluble, it does dissolve. On the right-hand side, it says, if a compound contains these things, it's insoluble, it does not dissolve. And so if we look at those rules, we see that nitrates and compounds that contain alkali metals, like potassium, are almost always soluble. So pretty safe bet that the potassium nitrate is the AQ, which means, of course, that the silver chromate is going to be our solid, our precipitate. So that is our double replacement reaction, and that pretty much wraps up these equations. Like I said earlier, if you're struggling with this, don't get too discouraged. This is going to take some practice. We're going to practice this more next week, and I promise you'll get better at it the more you do it.